Thank you. You know, it's a small world. Well, that's an expression that many of us have used at various times, but really the world isn't so small after all. About, let's see, 57 million square miles. But there was a time many years ago when the world was much smaller insofar as the land area was concerned, because then we had a giant ice cap which covered much of the northern hemisphere. About 28% of the land area was covered by ice. Now, gradually that disappeared until at the present time we have about 10% of our land area which is covered by ice, as we see here. Now, 2/3 of the ice is gone. The only clues that we have as to the way in which this ice has worked is to be found in the study of the living glaciers of today. And so to tell us of these rivers of ice, we have invited as our special guest on Science in Action the famed glacier priest who comes to us from the Department of Geology at Santa Clara University, California, Father Bernard Hubbard. Welcome to Science in Action, Father Hubbard.
Thank you, Dr. Harold. Ice is a very cold subject, but I find glaciers among the most fascinating things on Earth.
You know, this is about as close as I've ever been to a glacier. You know, it sort of has a river effect or a flowing effect.
Yes, in more ways than one, Doctor. That's the Great Gapach Glacier that I first studied in the Alps, and it is a real river of ice. Ice really follows practically all the laws of gravity the river does, only it's slower.
What are the three types that we have now? We have the Piedmont and the valley types?
Yes, now this is the valley type here, and just imagine that it gets out to the foot of the mountain and it spreads out. That's why it's called a Piedmont Glacier then, Pez and Mons, foot of the mountain. That's the second type, and then the third type we don't show here. It's really an ice cap.
I see.
In Greenland and Antarctic, those are the biggest ones today, and then we have lesser ones in Spitsbergen and Nova Zembla, Alaska, Baffinland, and so on. Those are just huge areas that are flooded with ice, so to speak. And here and there, out of the ice, come strange rock-like prominences called nunataks.
Nunataks, that would be a good word to remember. Let's see, these prominences then that come out of the ice are the nunataks.
Yes, Doctor, and they're just simply lifeless rock that comes up 2,000 and 3,000 feet sometimes.
Well, now, if we started our study of a glacier with such things as ice crystals, they'd look something like this.
Yes,
snowflakes.
Yes, the beautiful little crystals that we're accustomed to see, and they're beautiful hexagonals, that's the beginning of the glacier. Because when ice falls above snow line, and you know, snow line is actually the line above which ice is, you find snow all year round. In the equator, it's way up in the highest mountains. At the poles, it's almost down at sea level. But that's where this movement of ice then begins to form what we call a glacier.
Well, then eventually, of course, it packs down until you have the flow started, and then, of course, small boys know about such things as snowballs.
Well, that's our snowball, Carl, and actually, when a youngster goes through the process of making a snowball, he goes through all the processes nature does making a glacier. Because actually these snow crystals, they come together and alternate melting and freezing together with their own pressure, soon make a sort of a mass, something like frozen sludge, and then that starts in to just pour itself around whatever area it happens to be in.
Suppose we make a synthetic glacier with this river cut gorge, and we'll add our glacier material at the top here, and we'll watch it now as it flows down. Now this would be approximately, would it, what we would have?
Very much so, Carl. You see, this V-shaped valley represents terrain before a glacier or an ice cap has started to cover it. And then pretty soon, when this accumulation of snow comes to the condition where it starts moving, then the glacier is born, and it starts coursing down through this V-shaped mountain.
Well, suppose I add some color material right here, put it in a straight line, and we'll see the rate of speed with which it moves. Let's see, the center is moving out a little bit faster.
Yes, you notice that right away. That's why this is a very good example. There are two reasons for that, Carl. First of all, the center is much higher in mass than the sides, and that allows it to sort of have a forward thrust.
Yes.
And then the reason it's hardly moving at all on the sides here is because there is a sort of a frictional drag where you have the containing mountain sides that are just simply pressed against the glacier. That always allows the center to move faster.
Yes, and I suppose you'd have these small glaciers here in the various side places running into the main glacier there.
Yes, because presumably we just simply have a whole ice cap that's forming here, and they carve out the little cirques, and they knock off the depressions, and for that matter, they're always changing topography.
Well, suppose we look at a real glacier, as you have visited these many times, and see what it would look like as we watched it in motion. This would be what now? This is
right there, we're looking at the beautiful Mount McKinley, and the Muldrow Glacier is coming at us. That's about 90 miles long, and it constitutes one of the longer glaciers in the whole world. You see, literally, there are thousands of these smaller glaciers scattered around the world, the Himalayas, the Alps, Alaska, and elsewhere. They're just, as you see here, huge bodies of ice that are really moving.
Well, now, what would be the rate of speed of that?
Well, that'd be hard to judge because there's so many variables. But actually, every glacier moves from a few inches to a few feet a day. We seem to be the only things moving in the plain there. Yeah. But all this whole mass here is moving, and some glaciers, in fact, in Greenland, they go around 30 or 40 or even 50 feet a day on account of the pitch and the weight on them.
How many glaciers would you estimate there are in the world?
Oh, they go up into so many thousands, I don't think they've ever even been counted. They're generally, they keep on going until they come down to levels where temperature offsets further advance. And then they either start rivers, or if they come into seas or lakes, they break off into icebergs.
Well, now, we started with this first model and the very sharp sides, and then as the glacier moves through, it chews out material, and eventually we end up with something like this.
Yes, there's the typical U-shaped trough that is very characteristic of glacier action.
That is, this U would be right down here.
Yeah, and practically all the way along with steep sides, particularly as you notice there. And here you have your mountains rounded off. Everything has been smoothed and rounded off. All the projecting ridges of the first table have now been smoothed, which is the erosive effect of glacier ice.
Well, now, as that glacier moved down the valley, of course, it picked up things such as this, and part of that scouring action, I gather, is due to this rough surface here.
That and particularly weight. Just like if you drop a hunk of soap in the sand, it gets all covered with sand, and then let it dry, and then try to wash your hands, and you'll have the same effect that a glacier has. Striations and just about everything that you don't want.
Well, now, these look as though they might have come from a stream bed, but I gather that's not the case.
In this particular case, they could have come from a stream bed, but actually this one came from the Mendenhall Glacier moraine, and this beautiful stone here, notice how polished and round it is, and it's rather heavy.
Yes.
Well, actually, that was under this tremendous weight of thousands of tons of ice, and it just couldn't move up or anything, so it was just moved around and around, scouring a sort of a glacier mill in the bedrock until finally we had this result.
Well, now, one of the results of this glacier moving down is to make these scratch marks, and I see some tremendous scratch marks here. Is that your jackknife that I see there in the middle of that one?
Yes, that gives you a little comparison in size, Earl. And those scratches simply indicate here that when the ice passed over that, it had some rocks in suspension in the ice that were harder than the bedrock, so they scratched. Otherwise, if they were softer, you'd find that they'd simply pulverize themselves up into a sort of a dust, which would be carried away from the glacier in streams.
Now, in the central part of the United States, I know we have some peculiar structures, sort of hummocks, and they are very, very interesting. Perhaps you give us an idea with this model here, just what's involved in those.
Yes, those hummocks we just were looking at were taken again in Alaska. They call them in the Alps roche mouton, or sheep's backs.
Yes.
And here's the way they occur. You find some kind of an elevation in bedrock. The glacier comes to that, and instead of diverting around it, being rigid like ice, it begins to climb over it, and then the buffing action makes everything rounded off. And then with a little imagination, when you see a whole lot of them together, they give the impression of sheep's backs. That's where they got the name.
Well, you glacial geologists have some special words, and one of them that we quite often see is this word moraine. So I'd like to point out just how that is spelled, and perhaps with this glaciated valley now, you can give us an idea as to what a moraine is. With these small pebbles here.
Well, first of all, the substance of moraines are merely the rocks that have been chipped off from the sides of the containing rock mountains, let's say. Now, a glacier's action is very much like a conveyor belt with rocks on it. So when it goes along, let's say it stops here. All right, the conveyor belt still pulls the rocks along, and a whole lot of it gathers up. Then let's say a recessional period comes, the glacier moves back. It scatters rocks all the way, and then it's stationary again, another one builds up.
Oh, yes.
And then in that way, you can have successive ones where you don't have any ice at all today, but that proves that ice was once there.
Yes, and that would be an example now of such a thing as we see here.
Yes. Those would be... that, in fact, is a terminal moraine on one of the Alpen glaciers, and it's, you see, a terminal moraine does not have to be down on the bottom of a trough.
Oh, I see.
It's really hanging on as this one does on the side of a mountain.
Well, now, you can have moraines that are along the side also, so if we were to, drop some these pebbles along here, we'd have the same action?
Well, yes, but then you have to imagine this is icy, and then the ice always pulls away a little bit from the side of the containing rocks, And when the rocks fall down, they're gathered right where the ice joins the rock, and then they're ground up and ground together and make scratches and powder and just disintegrate.
And that would be such a thing as we see here, this beautiful moraine on the side here. This
yeah, see on the left-hand side as we look at it, those are moraines that have been piled up very similar to the action of a bulldozer. Because a glacier doesn't just shrink all at once. It oscillates a little bit up and down and keeps pushing up like a bulldozer all the time.
Well, now, a glacier goes forward, it drops this moraine, this pile of rocks, it comes back, it could go forward and drop another one right on top of the old one.
In fact, that usually happens because we've had all kinds of oscillations even in the formation of the ice ages. Now, in this particular case, we're looking here at a terminal moraine on the Mendenhall Glacier. This moraine was caused by the first glacier there, let's say. And then the glacier moved back and a huge forest grew up.
Oh, this looks like a pile of cannons.
Yes, because the stream that eroded that little trough there left them sticking out of the sides. Now, another picture that we'll have of a close-up here shows one of those particular stumps. They were called pre-glacial stumps when I first went up there, but I found that they were interglacial because the roots were ground around, meaning they were entwined around morainal rocks.
Yes.
So the moraine had to be there first. And then the top of that picture, you'll notice the shear action because the actual movement of ice is not fluid, but actually hexagonal crystal over hexagonal crystal.
Yes, well now,
that shears.
one thing, let's see, we have been speaking of glaciers receding. By that we don't necessarily mean that they have been moving backward. Actually, they are melting on the front end faster than they are being built up at the back end.
Yes, exactly, Earl. It's a case of where we can demonstrate that a little bit. You see, when evaporation exceeds precipitation, then although there's always a forward movement in the glacier, yet there is a shrinking backwards. Now, this is just a little piece of wax. We had to make it awfully thin because that's the only way we could make it work. Now, I'm constantly pushing that forward, notice. Constantly going forward.
And as you go forward, then the same sort of thing that happens in a glacier.
It's still going forward, but as it meets this heat, notice my hand's getting closer and it's melting, but it's always going forward.
Yes.
When movement ceases in a glacier, it's no longer a glacier.
One thing that I've been wondering about is how you can have enough heat in such places as the far north to melt these glaciers.
Well, Earl, it isn't so much a question of heat as a question of time. And actually, in the summertime, it does get reasonably hot up there.
Well, suppose we step over and look at these twin glaciers, because that's something that I was admiring a little bit earlier. Those rings there look much like the sort of thing that you would see in the cross-section of a tree.
Yes, and I believe the tree rings are sort of chronological, don't they?
Yes.
Well, that would be the same effect here, even. You see, off to the left, where we can't see in the picture, there's a crack in the mountains, and the winds that blow down from the big Taco ice cap just pour debris and dust and pollen and little objects across the glacier, and when they're very similar to what you showed on the demonstration model.
Yes.
And then the center moving faster than the sides. Now, in winter, snow falls and no dust can blow. So that's why you have those alternate bands of black and white that indicate seasonal changes.
But during the summertime, the protective covering over the top of this dirt isn't sufficient to prevent the ice from melting underneath.
No, not unless it's a terrific covering or like a volcanic eruption or a landslide. In fact, small objects, especially dark objects, hasten the melting of a glacier.
Yes, you were mentioning this experiment you conducted with a piece of a leaf and a quarter, I think it was?
Oh, yes. Actually, I could have put $1 on it, it would have the same effect, but it didn't have $1 in that time. The quarter did it. You see, the quarter is a metallic and light colored. The leaf in fact, it was a rotten leaf too. If you touched it, fall to pieces. It was dark. Now, light objects attract light, and dark objects repel them.
Oh, yes.
And so a dark object will work right down into the glacier several inches, even though it's made of such a little friable material as a leaf, whereas the metallic coin stayed on top because it was light-colored.
Well, how would you go about telling the temperature, say, on the inside of a glacier?
Well, that's a little bit more involved. But we actually tried an experiment once in lowering one of the young men that was of the party down into a glacier crevasse. It was a rather risky thing to do, but we felt, though, that we were taking no unreasonable chances. After all, you take a reasonable chance when you're crossing a city street with the light, not against it. Oh. That's dangerous.
But this
see, we're letting George down the crevasse. The reason was we were three of us that were 200-pounders. He was over only 150, so he had to go down. Now, all the way down, he stuck temperature thermometers in holes all along in the ice. When he got out of sight, he yelled that the ice was so hard that he couldn't even stick a pick in it, which was correct. And then we formed a theory from that for about every 50 feet of descent into glacier ice, you get 1 degree lower in temperature. Now, this has built up quite a number of following theories since then.
What I'm wondering about now, working over these crevasses, it looks to be very dangerous work, but what has formed the crevasses in the first place?
Anything can form them of many causes. An earthquake could, sudden changes in temperature, but what you're looking at here, Earl, that's due to a bump in the bedrock. And when the ice flows over that, it causes a crack to go from top to bottom, several hundred feet, even 1,000 feet or more. It may only be about a half an inch wide, but it yawns open and closes again with a slow movement of the glacier as it goes over that bump, and there's no longer any strain.
Those must be extremely deep there.
Yes, some of them go down several hundred feet, but then they zigzag down like forked lightning. And at the bottom, usually the snow pushes, the ice pushes them together on account of its own pressure.
Well, now, to be able to go down and crawl over such types of ice, you have to have very special equipment. And I see those
we're taking it
things
off
on the bottom of the shoe. That's something that's quite interesting. Perhaps you'd give us an idea as to what's involved in that. I know you have preferences in this type of equipment yourself.
Oh, yes. You find what suits you better than others sometimes. Now, this is an ordinary pair of crampons or Steigeisen. And notice these are rather long spikes. Personally, I prefer the little pyramid-like spikes because sometimes we've been on glacier for 60 or more hours and you get tired.
Yes.
And these long spikes, you're liable to not lift your feet up enough and trip. And you're only allowed one accident per lifetime on a glacier.
Well, then you'd want to have a very trusty ice axe to use also.
Yes, with these ice axe, we cut steps where otherwise our shoes wouldn't hold.
Yes.
And then this long pointed portion here with the reverse sections. When you can't jump a crevasse, it's too high, you simply dig it in and then muscle yourself over and pull, knowing that that'll hold. And then you can get to your objective, whatever it happens to be.
Well, I can see that there's a science involved in this all in itself. One thing I'm wondering about, are these glaciers now, are they growing at the present time?
For the most part, Earl, ever since about 1857, all the glaciers in the world have been receding or shrinking.
Yeah.
However, there are some cases where they've been going forward. Now, there's one in particular.
This is hole-in-the-wall?
Yes, this is called the Hole-in-the-Wall Glacier in Alaska, and when I first took this picture, it was 1927, where you see a glacier going into a lake and then a little forest and scraped rock in front of it. Now, if you go back to the same place, you wouldn't see anything in front except ice. Oh. That has been going forward prodigiously, about 3 miles or more in the past 5 years. So that glacier is really advancing.
And how about twin glaciers?
Well, twin glaciers make an interesting study, too, Earl. There's a picture I took in 1927 of twin glaciers. You see, they come down from the Big Taco ice cap, and if you notice, they join together in front in about a 3-mile-wide berg-discharging front of ice. In 1929, it broke. And then when I took my last picture of it, just a few years ago, you can see the twin glaciers have completely altered their shape. They're way back in the mountains now, 5 miles away from where they were when I originally took them. So the Hole-in-the-Wall Glacier on one side is advancing, and these two are retreating. So it shows you that they're a little temperamental, too.
Well, now these glaciers move downward, and eventually they come to the sea. What happens then?
Oh, then is really one of the most dramatic, cataclysmic acts of self-destruction I think you could ever hear of. As soon as the glacier enters the sea, it's buoyed up, of course, in the water, suspended. And from then on, you find that the top begins to crumble. Every little while you'll hear a roar like a cannon, and then pieces will start in to break off. And so we went up right close to this glacier in Yakutat Bay.
Is this Sawyer Glacier?
No, this happens to be the Hubbard Glacier here, not named after me, but another rascal named Hubbard. And it's breaking off now at the proper time. Timing has everything to do with it.
Taking a boat in there must be pretty risky.
Well, we have a stainless steel boat, and that can go through anything.
You know, those are falling very, very slowly.
That isn't slow motion, Earl. You'd think it was, though. But if you'll follow one of the pieces down when it starts to fall and count seconds, you know at the rate of 32 feet per second, the acceleration, you count 4 to 5 seconds in some of those falls. That means that wall is about 400 feet high.
You know, one thing we hear about is this idea of a person speaking, and some of that falls off. Is that right, the sound of the voice?
No, that's a big decimal point. Actually, one time I put some naval guns, had some naval guns shoot 5-inch shells into a glacier, no effect. I put a case of dynamite under one corner, thinking I'd get a nice picture. Just a few chunks fell off. It is the tidal range that causes these glaciers to rise and fall.
Tidal fluctuation, then, is the important thing.
That's the most important thing as far as icebergs are concerned.
Look at that go down.
Yes, they not only go down continuously from the top, but pretty soon you'll see something else start to happen.
Well, now, let me pose you a problem before we go on this. Now, all of this is breaking off the top, and so there must be ice going out underneath the water. What happens to it?
Yes, the same portion that's on top is also underneath. And as it breaks off from the top, the shelf underneath is still solid, and it keeps pushing out, and then eventually it breaks off, and look what happens here.
Well, it comes right up out of the water.
Yes, a whole big dome comes up in one piece and doesn't break off because all it has to do is just simply get out of the water without breaking.
What would be the size of that piece?
Oh, that's a little chunk about the size of the Capitol building in Washington.
And, of course, only 1/7 of this is above the water, and all the rest is beneath the water when it floats, that is.
Yes, that's the, then in salt water, that's the normal condition. And when they do break off, as you see here again, it's all like slow motion. The part underneath breaking, coming up, turning over to assume its equilibrium of 1/7 above, 6/7 below. And then as you see here, sometimes the city square blocks in area, they float out to sea.
And then eventually, I suppose, they get into warmer climates and then they're dissipated.
Yes, because the convection of water is enough to cause them to be eroded underneath, and pretty soon they disappear.
Well, Father Herbert, I know that you've brought back much valuable information from your various trips. Are you perhaps planning another one sometime soon?
Oh, yes, Earl. You know, if you keep going all your life, you live a long time.
Well, I hope that when I'm 66 years old, I'll be able to make some trips into Alaska. You were mentioning these orchids that you found.
Yes. You know, very few people realize that along the Alaska Peninsula, you have probably one of the longest chains of volcanoes in the whole world. They're average 35 miles apart for about 2,000 miles. And they're connected with glaciers, too, because I found some huge volcanoes have blown out big holes and left a crater glacier where they had been before.
Well, I see our time is growing short, but Father Herbert, before I say goodbye, I want you to promise that you'll come back and tell us about your exploration in glaciers and in volcanoes this summer.
We'll try to, Earl. We'll have to warm you up after all this cooling off.
Fine. Thanks a lot.
Thank you.
Now, all of you space cadets, get your equipment together, because on our next program, we're going to talk about the problems involved in survival at high altitudes. In other words, how you would live up on very high mountains, and secondly, what you would do about survival when you're traveling at very high regions in space. Our special guest, Dr. John Lawrence, University of California, Captain William Orlov, U.S. Air Force. We hope you'll plan to be with us then. Thanks a lot.